Our topic for today is energy conservation. What happens to the energy of a ball when you throw it in the air? It also starts to change. As the ball goes higher, what happens to its kinetic energy? And what about its potential energy? So, as we're moving up, the kinetic energy it's less going up, more going down. Potential energy is more going up and less going down. And so while this might seem, kind of confusing, we're going to get into this topic a little bit more so you understand what's going on. So what happens to the kinetic and potential energy when the ball comes back down? Well, when you throw the ball in the air, the energy transforms from kinetic to potential and then back to kinetic. So we have the most kinetic energy at the bottom when it was moved the most. And here we have a lot of potential. Remember, at the very highest point, that's where we have the most potential energy, the more stored energy. And it makes sense that at that very top point, it has the most potential to come back down. So the law of conservation of energy states that energy cannot be created or destroyed. Energy only gets converted from one form to the other. And so here we're dealing with either potential or kinetic. And also mechanical energy. One of the most common conversion is the changing of potential to kinetic, or the reverse. So in a closed system, the total mechanical energy, and sometimes we abbreviate that as TME, total mechanical energy, is equal to the potential plus kinetic energy. Okay, and that makes sense because it's all moving energy. So mechanical energy is due to an object moving, or its position, its movement. So total mechanical energy is potential energy plus kinetic energy. Or we can also write this as TME equals 1/2 mv squared, because this is your kinetic energy formula, plus mgh, which is your potential energy formula. So this picture is very, very good. For example, on the very top, we see our kinetic energy is 0 because we are at rest. So we're not moving, so our kinetic energy at the top is 0. And so that means our potential energy at that point is 100. Makes sense. We're at the very top point. That's where we have the most potential. So if we wanted to calculate our TME, our total mechanical energy, remember it's just kinetic plus potential. So here our TME would be 100. TME here would be 100. 0 plus 100 is 100. Again, now it starts to come down and our kinetic energy starts to increase because we're moving, and our potential energy goes down because it is halfway here. Okay, but our TME still remains 100. 50 plus 50, 100. At the very bottom point, we see that we have total kinetic energy. It keeps increasing, but our potential is 0. We have no potential energy. At this point, our TME, it continues to be 100. And KE at this point starts to decrease again, and we're starting to get a little bit more potential. But even at this point, our total mechanical energy is still 100. And so this very top picture explains a lot of what we're going to be doing in the classroom. So make sure you review this topic. And again, just like the science of sledding, we have the most potential at the top, and then in the middle we have both of them equal to each other, and then at the very bottom, kinetic energy takes up the most of the energy. But if you notice, our total energy is conserved. It never changes. It's always 100 towards the entire thing. So a golfer hits a 0.4 kilogram golf ball with a speed of 0.4 meters per second to a height of 30 meters. What is the golf ball's total mechanical energy? So first, let's write our variables down. M is 0.4, velocity is 0.4 meters per second, G is always going to be 9.8, and our height is 30 meters. So we have all the info we need to find total mechanical energy. So first, TME is equal to 1/2 mv squared, so 1/2, we can plug in 0.4 for mass, and 0.4 for velocity, plus mass is 0.4, G is 9.8, height is 30. So when we multiply and add these together, we get 117.63 joules of energy. A bowling ball is attached to the ceiling. If you let it go from holding it right in front of your face, will it swing back and hit you? No, so the total energy never exceeds the starting energy. So it can't, magically obtain energy from the system and end up hitting you in the face. You can't, that won't happen. So what is happening to the energy in this system? And where is potential energy the greatest? So energy, remember, is always conserved, so it should be the same all throughout. So where is potential energy the greatest? Where does it have the most potential to move? And so your answer here should be 2. That's where it has the most potential energy, because it could have the potential to move to 1 or to 3. So that means that our greatest kinetic energy, where it's moving the most, it would be 3 and 1. Remember the law of conservation? Energy cannot be created or destroyed, it can only be converted. And so because of this, the initial total energy is equal to the final total energy. And so we can write this like this. Potential plus kinetic plus potential initially will equal its final potential and kinetic energy. Another way to write this is this long equation, which is just the same equation but written out with all the variables attached to it. So Julie has a mass of 49 kilograms. So make sure you're writing your variables down first. What is her potential energy when standing on a 6-meter diving board? She is 6 meters above the water. Julie jumps off the diving board. What is her kinetic energy just before she hits the water? So first of all, let's find our gravitational potential energy. So GPE, remember, is mgh. So our mass is 49, G is 9.8, height is 6 meters on the board. So we find that our gravitational potential energy is 2,881.2 joules. This is her initial potential energy when she's on top of the diving board. To find what her kinetic energy is just before she hits the water, first of all, we have to realize that our kinetic energy initially is 0, right? Because our gravitational potential energy was this amount, 2,881.2. That's where she had the most potential energy and the least kinetic. That means on the final side, she has the least potential energy. So let's draw her right here in the picture, and you should have that picture on your paper as well, so we can see what I'm talking about, so we're not confused. So at the very top, she has the most potential energy and the least kinetic energy. That's why we said the most is what we calculated, which was 2,881.2, and the least kinetic energy, which is 0. So when she falls, okay, at this point, when she hits the water, she has the most KE, most KE and the least PE. And so when we say least PE, that is equal to 0. And so here we have our initial, right? This is KEI plus potential energy initial equals KEF plus potential energy final. So kinetic energy 0, just like we said here, plus potential energy initial, which we calculated, equals kinetic energy here, this is what we're trying to figure out, and potential energy at the very end is 0. Okay, so we can cross these out in our formula, and so we find out that our kinetic energy final is equal to our potential. So potential at the top is equal to the kinetic at the bottom.